Okay, so in the tools software Slack channel, the latest message is some instructions for how to set up a Conda environment. Do people have Conda installed on their laptops? Yes. Okay, good. So if you don't have Conda installed, it should still work. The problem is that, so okay, this is a bit of backstory. So Starry is built on Theano, which was the first generation of these cool machine learning tools that do back propagation and let you do fast inference. And so it's like just-in-time compiled Python code, compiled into C. Theano died. Theano is no longer supported. And unfortunately, the latest release of NumPy breaks compatibility with Theano. So I think if you have a NumPy that's earlier than like 1.21, it should be fine. If you have a newer version of NumPy, I recommend the Conda approach because then you're just in an environment where all the package dependencies are met. If you don't have Conda, just pip install NumPy 1.21 is my recommendation. And if you need help with that, ask a friend or ask me. I'm happy to help too. Questions about that? Yes.
Wouldn't you want to install NumPy 1.20 if 1.21 breaks it?
I think 1.22 breaks it.
Oh, okay.
I'm actually not sure. 1.20, great. 1.20 it is. In the environment, you'll actually
1.20 is in the
1.20. I'll also say that, especially after seeing Dan's tutorial yesterday on JAX, I'm convinced I need to rewrite Starry on JAX. So that will happen sometime. Okay. So give me just 1 minute to set one.
On your own screen, right?
Yeah.
How's
I know
that?
it's not as convenient, but.
Okay. You don't have to do what I just did then. That's just like make the plots look nice. Okay, so let's start with Starry. So import Starry, and let's also import NumPy. So a little more information about Starry. So Starry is built on Theano, and the thing about Theano is it compiles the functions the first time you run them. And so the first time you run Starry, the first time you create a map and evaluate the flux or the rate of velocity, it's going to take forever. But the next time you do it, and even if you change parameters, it's going to be fast, I promise. Importing Starry might also take a second. Good. So, are people joining? Or?
Yeah, people are joining. I'm trying to figure out how to remove the.
That's okay. So let's, Starry can model photometry, but also spectroscopy. So let's start with talking about radial velocity maps, which is fairly new in Starry. And it's more pertinent to here. So what I'm going to do is I'm going to create an RV map, and that is just a starry.map object.
Is there somebody who's?
Yeah. Me.
Okay.
So whenever you create a Starry map, the first argument is the degree of the spherical harmonic expansion, right? So spherical Starry models stellar surfaces as spherical harmonic vectors. Let's do 15 because that's big enough to model things we might typically care about. The other argument that I'm going to pass is RV equals true. That's going to let Starry compute radial velocity curves. And again, these are radial velocity curves, or approximate radial velocity curves for the photometric effect of spots on the surface. The last thing that we're going to pass is lazy equals false. Lazy evaluation is what I've been describing. It's this Theano, similar to JAX, builds these computational graphs for all computations. And that happens in lazy mode. So in lazy mode, whenever you evaluate a cell, you don't get a number out, you get a graph or a node in a graph that you can then differentiate or that you can then put into PyMC3 to do inference. Let's not worry about that. Let's do lazy equals false. So when you evaluate the flux or the rate of velocity, you're going to get a number out. It's going to compile the function for you on the spot. Okay. You might get some messages. Yes, question.
Quick question. The RV equals true. Does it turn off the flux?
It doesn't, no, it adds extra knobs, yeah, good. So the first thing we'll do is let's just add a spot on this. So the map is just the surface map of the star, let's add a spot, and so that's the spot function. The arguments you can provide are something like contrast. This is fractional contrast, so contrast 0.5 means the spot is 50% the brightness of the rest of the photosphere. A radius, I'm going to do a radius of 20. This is in degrees. Just for you to have a sense, a spherical harmonic expansion of L equals 15, you can model things about as small as 10 degrees on the surface. Sunspots are much smaller than that, and so you'd have to go to higher order in starry. There may be numerical issues if you try to get to too high a degree. So let's stick with large spots for now, and these numerical issues are something that I'm still thinking about. You can also specify the latitude and longitude. Yes.
What degree is that? Just so we know. Like
What degree is what?
Like what degree is about too high that you'd get into machine precision?
Don't go above 30.
Okay.
In L in spherical harmonic.
Those you get into.
Yes.
Radius of 20. That means that. What does that mean exactly in terms of relative size of your feature with respect to the star? Can you say it again? Like 20.
It's 20 degrees on
20 degrees on the. Okay.
You'll see.
Like different, like, yeah. Okay.
You'll see what it looks like in a second.
No, see, fair enough.
So let's put a latitude of 30 and a longitude of 0. And you'll see that you get a little message compiling spot. And so it's compiling the C function that adds the spot. Because it's the first time you guys are running this, it might take a little longer. And then let's just see what we're dealing with. And so we can use the show function. The show function takes a few arguments. One of them is projection. Your options are rectangular, orthographic, or mole-wide. We can explore those later. Let's just do rectangular, then it's just a latitude longitude grid. I'm going to provide the RV equals false keyword here so that we're actually looking at the intensity map, not the velocity map of the surface. And then finally, I'm going to do color bar equals true just so we see what the normalization is. So, Baptiste, that's how big this spot is. It's a fairly large spot. Just a quick note about normalization in starry. You'll see that the yellow portion, so the background of the star is at 0.3. That's actually 1 over pi. And the reason is that if you integrate 1 over pi over the unit disk, you get 1. And so that's the normalization in starry. So if it's a featureless map, it has a flux of 1. Good. We can also do orthographic projection. So just ortho for short. And that'll show you, okay, so this is the velocity map. So it's featureless. So let's do RV equals false again. And that'll just show you what the star looks like on the scale.
What's the RV featureless?
Because they haven't assigned an equatorial velocity to the star. I'll do that shortly.
Can you change the phase at which you look the star? Kind of.
Yes, you can. You can. So I'm going to do 2 things actually. So the first thing I'm going to do is I'm going to incline the star. So I'm going to give it an inclination of 60 degrees. And then I'm going to do rvmap.show RV equals false. And I'm going to change the, like you said, the angle at which I see the star. So let's look at it at a rotational angle 30 degrees. Is the pace okay? Am I going too fast? Should I slow down?
I've copied your code exactly, and I've just got a plain featureless orthographic thing.
Are you sure you put
Did you do
RV
RV equals false?
Yeah, I've got RV equals false. I'll hold it up to the camera.
I'm getting the same thing.
At least it's not just me doing it.
But the second one is working fine.
Yeah, I've got this one fine. Same object. Body control.
I think he's already made versions of this.
Which way?
It's got a little bit of something around here. Maybe that's
I've got a different.
When you got like 40 people, like, I don't know, it's like,
How does this change?
just got loose.
Yeah, I wonder. Because I mean, it's really the same.
Did someone else get this as well?
I don't. And my rectangular projection seems a little bit different than yours.
I do have like everything else is the same.
Might be just.
Yeah.
Yeah. It's really different.
Well, I don't know.
I'm sorry.
What that would do to like the Earth if you just like.
Okay, I ran it again and it worked. So
I'm getting a different weird thing also. So my rectangular projection is different than yours.
you probably ran.
I'm gonna research Chrome.
It's like, it's not like,
Every time you run
it's
a
not
spot,
like
that's
the
a
sun
new
is like
spot.
squished by its
Seems like you're out of two
or something, in which case maybe the like gravity differential would do something, or take the orbits.
It just. I'll get taking.
All right.
I still don't
Okay.
the color.
You still don't have what?
Wait, would it change the like solar,
URV equals false.
like the magnetic field orientation? Would it change how like charge particles outside the solar?
Yeah, I think
It's expected behavior. I'll get to the RV in a second.
Oh, okay, yeah.
The thing, I think you just have to reset it back to just it from top for that. So I didn't solve the problem.
Okay, good
So
to
I
know.
think it might just.
It's like the dynamic.
Okay. Good. The other thing you can do is, so you can change theta to be an array. And then it gives you an animation of the star with you. Oh, so depending on whether you have the appropriate MPEG backend installed.
Oh,
Yeah.
okay.
Okay. So if that didn't work, don't worry about it. But ask me later. I'll show you how to install.
It's a.
So if I do RV method, I'll show RV equals true. It's also,
No, because that's not included in the environment.
I get nothing. And that's because I haven't told Starry what the velocity, rotational velocity of the star is. And so in order to do that, it's just VEQ property for equatorial velocity. And so let's give it an equatorial velocity of, I don't know, 30 kilometers per second. Pretty fast, but just as an example. Then if I run the same cell again, you can now see that what we're showing here is the velocity weighted intensity map of the surface. And so the colors correspond to blue shifted, red shifted, so negative velocity, positive velocity. And if you're able to animate it, you'll see that the spot imparts a signature there. So like you have less blue shifted emission as the spot comes into view, less red shifted emission as it goes out of view. Good. Okay, but we're not here to make pretty images. We're here to do science. So let's compute a light curve and let's compute an RV curve. And so I'm going to redefine my theta here to go from negative 180 to 180 so that the spot is centered. And then I'm going to compute the flux simply as RV map dot flux theta equals theta. That's just what's the flux from this star up here. Sorry, let's go back on a second. What's the flux from this star photometrically as it rotates?
And Rodrigo, you set the inclination at an early stage, right?
I did. I'll scroll up to it here. It's an inclination of 60 degrees. Back down to the cell. And then I'm just going to plot theta, flux, and I'm just going to normalize it. So I'm going to divide by the mean flux. And, well, yeah, let's run it. Compiling the flux function. There you have it. Okay, so the spot comes into view, it's at the minimum, and it goes back out. So single spot, light curve.
That's a big spot.
It's a huge spot. I can also compute the radial velocity or the approximate radial velocity that I'd measure. Now note that I don't have any spectra here. I'm not. We'll get to that later. But an approximate way to compute the radial velocity effect of a spot on a star is to compute the integrals of the velocity weighted intensity normalized by the integrated intensity. And so what that looks like in starry is you just compute RV, theta equals theta. And then we can plot that.
You do this.
And lo and behold, it looks kind of like the derivative of the flux. Yeah. It sounds familiar. I don't know where I heard it. Yeah. And we can convince ourselves of that by, you don't have to follow. I just want to show you. So, so I just computed the gradient of the flux and I'm normalizing it to the same scale as the RV curve. And then I'll plot both of these. So they're similar, right? They're morphologically similar because there is a phase shift. I don't know if it's the same phase shift Annalise was talking about yesterday, but maybe it's related, but these things peak at different
So
times.
now you should do FF prime.
Yeah, because it's the product.
Yeah.
Okay.
So in the line that's F prime multiplied by flux.
Oh, very similar.
Can you briefly scroll up for a second? Oh, okay. Interesting.
Maybe that.
It's possible.
Oh, wow. Wow. That just blew my mind.
No, we were literally, I literally asked on the Slack for the justification that it was the quadratic form. Boom.
Wow.
Face.
Very cool.
Suzanne was
Well, me
like.
too. I mean, it means.
I like that Suzanne's reaction. Your live coding is that she must be your live coding.
No, but the point is, FF prime is an approximation that treats the spot as point-like.
Yeah, right, yeah. So
A big spot.
it should become even better if you made a smaller spot.
Yeah.
Well, yeah, I mean, they're not perfect, but that's really
That's really good. That is sick.
And obviously the other thing that I'd be keen to play with is that does it still, how badly does it break You have multiple spots at different places.
Mhm.
I think it, because
It will break, right?
Because the RV is so much more information than the flux. And so you can't gain information by just taking a derivative.
Right, but that's very relevant to the discussion.
Yeah,
After
yeah.
the discussion.
But that's a good thing to play around with space, right?
Yeah.
Okay, questions about what we just did? The people, yes,
It's not worked together.
it's totally broken.
I get something for the flux, and we both get something for the flux that looks more like the RV, but even when I'm normalizing by the mean, the scale is 10 to the 17.
Okay,
Yeah.
let's chat afterwards. If you This may be a bug in Starry. I mean, your environment might be weird or something. I'd love to fix that. Okay, this is one way of computing the approximate radial velocity effect of a spot. Another one is to actually model the spectrum and model the shape changes to the spectral lines and then compute the radial velocity from that. So let's do that using Starry. So is it okay if I move on?
Can I just ask a question?
Yes.
So, since magnetic fields is no longer the word you're not allowed to mention, what about limb darkening?
Oh, you can add limb darkening, sure. That's a good question. So what I would do here is, so technically this first number here, the 15, is called y-deg. It's the degree of the YLM, or spherical harmonic expansion. You can also provide a u-deg parameter, which is the degree of the limb darkening, u being the letter they choose for the coefficients of. And so when you do that, you can then, sorry, you don't have to write all this down. I'm just doing this to answer the question. So the limb darkening coefficients, you specify them by directly indexing the map. And so index 1 is U1. And so we can give that like strong linear limb darkening and quadratic limb darkening.
At least the first part is.
And compute the flux. Doesn't work.
Is it because it started zero?
No.
Well, I didn't mean to break your thing.
Is it?
It worked for me.
You didn't run the cell where you. Yeah, you didn't run that.
Yeah, you didn't run the cell with the.
Correct, where it didn't, yeah. So I reinstantiated it. I need to add a spot.
Yeah.
And I need to change the inclination.
It's the notebook.
Yeah.
Welcome back to the notebook.
See, now it's limb darkened.
Sick.
Yeah.
Nice.
Damn.
And you can compute the flux here. And
Since Eric Ford isn't here in person, I would say you should be using Pluto notebooks.
I know, I've messed up the entire.
On behalf of Eric Ford.
Yeah.
You can see that they're slightly different. This one's a little more V-shaped than that one, I think.
Yeah,
That's how you do them.
that was sweet, Rodrigo. That
So sorry,
is very well engineered piece of code.
where did you dig go?
Where?
Where did we put that one?
Okay.
Oh, okay.
Again, so I have a version of this notebook that runs properly and is not all messed up, and I'll put that on Slack. So if you're still behind, you'll have that available to you in a little bit. So let's actually model the spectrum. And so what I'm going to do is I'm going to create a synthetic spectrum, just a Gaussian absorption line. So the first thing I'll do is I'll create a wavelength array. And the reason there's a 0 there is because it's the rest frame of the star, so before rotation and Doppler broadening. And so, I don't know, there's some line of iron that's centered at 643 nanometers, I think. So let's...
You're literally the only person in this room that uses nanometers.
Not an observer, is it that obvious? Yeah. Good. And let's make our spectrum, again, 1 minus a Gaussian. So let's just picking some random amplitude here. And a random, well, not random, but somewhat physically motivated standard deviation. I forgot the square. Good. Okay. All right. So let's assume that's my spectral line in the stellar rest frame.
They're objecting to your line shape over here.
What's that?
They're objecting to your line shape over here. There's a chatter.
What are the headed tails or something? Everything to me is Gaussian. So.
It would only be a mixture of Gaussians anyway if you tried to make it work.
Right.
Can't you make a C-shaped bisector?
Sure, I could.
No, I'm not asking you to do that now. I'm going to derail it.
Okay, no. Not gonna do it. Good. The other thing I'm gonna define is so this is the wavelength frame in which like the line is emitted, like in the stellar atmosphere at 0 Doppler shift. So I'm also gonna define an array that's the wavelength grid on which I observe the line. And so let's do this. So you'll notice that it's a slightly smaller wavelength array. And the reason is that when you Doppler shift things, you need to define your rest frame spectrum on a longer grid to get rid of edge effects, essentially. And so let's say that it actually doesn't matter what numbers you put in here, but these are pre-vetted to work. Good. And now let's create a map. So the function that we want is starry.Doppler map. Again, the first argument is the degree of the spherical harmonic expansion. I'm going to pass in these arrays. Again, WAV is the observed wavelength grid. WAV 0 is the wavelength grid of my reference template spectrum. The other thing that I'm going to pass in is the number of epochs at which I'm going to compute the spectrum. NT for number of times, number of thetas. I defined a theta array up top, and so I'm just going to do len theta. I'm going to evaluate things on the same theta grid. The other thing I'm going to do is for convenience, or just shorthand. So remember that I explained this in the documentation, and thank you for saying this is really well engineered, but I think it's kind of clunky. If you index a map with one index, that refers to limb darkening, because limb darkening is indexed by U1, U2, and so forth. If you index a map with two indices, those are the spherical harmonic L and M indices. And so what this is doing is saying, I'm going to take all the spherical harmonic coefficients of RV map, and I'm going to set the Doppler map's spherical harmonic coefficients to that. So this is really just copying over the map coefficients. It sounded like a good idea when I was developing it, but and once you get used to it, I think it's fine, but it takes some getting used to. Okay, I am also, what time is it, by the way?
10:40.
10:40, okay, gosh, okay. I'm also gonna give it an inclination like before, 60 degrees is my favorite. Again, I'm going to give it an equatorial velocity, 30,000. And
To do dotting.
You're gonna,
what?
equals 60.
Points ink.
Thanks. And then finally, I'm gonna assign the spectrum that I defined up top. Press enter, cross your fingers.
And that's the RV map that you made up above with the spot in the left arc.
The only thing I copied over was the circumharmonic expansion of that spot. Yes.
I'm getting a whole bunch of.
Errors.
When I first compiled stuff.
Are you running in that? Good, yeah. Oh, you're on Windows, interesting.
Yes.
That is hard. Yeah, but, who's on Windows?
Well, I'm gonna put my hand down. If no one else is.
Oh,
Well,
yeah.
has it been? Suzanne's on Windows, she's getting weird errors. Has it been working for you guys?
No,
Okay.
just the piano part though.
Yeah, yeah.
Good to know. I'm sorry about that.
Piano doesn't work on.
For me, except
I think it does, but it's probably one of those compatibility issues.
the animation, it is working fine.
Which is a pain in the ass.
Yes.
Yet another reason to go to Jack's.
Okay.
No, Jack's just straight.
And I was like,
But it works on the Windows system for Linux.
Yeah, exactly. I mean, I'm not running directly in Windows, right? I'm running Ubuntu on the.
Oh, you are.
WSF. So it should be just like any other Ubuntu system.
Yeah.
Okay, let's chat after. So this is, I'm sorry about this, but this is super helpful for me. 'Cause now I know what I need to fix. Okay.
Oh, it's can't find G++.
Okay.
That's what
Yeah, but it's like, I should write some documentation on like how to help people running into these issues. Okay. Were people able to instantiate this map? Good to compile? Some people are nodding. Good. The first thing you can do, the cool thing, so I spent a lot of time with Doppler maps. There's this cool visualize function.
I'm not right now.
I'm actually going to zoom back out.
If you just copy and paste the down underneath.
And this is another one of those things where it might just break on everyone's. It's using, do you guys know Both? It's a Python package for visualization and uses JavaScript to render it in HTML pages. So this is going to take a few seconds.
I thought it was cool though. It's very good.
Yeah.
But I've only ever read it. No, but I think it is Boca. That's what it is for like pictures.
Just to irritate you. Emily Skip got you the actual spectrum.
Thank you.
Okay, I was off by,
You were way off. You were off by 0.1.
I'm off by 1 angstrom.
Yes, you're off by 1 angstrom.
I'm sorry.
No, I appreciate it.
You get an amendment.
Thank you.
Is it
Okay. So, if you're one of the lucky people for which this work, what you now see is a couple things. Over here, you see the mole-wide projection of the star. And so if you have a trackpad and you scroll up and down on the trackpad, you are seeing what the surface map looks like at each wavelength. And so in the center of the spot, the star is darker everywhere. Outside of the spot, the star is brighter. And then if I move my mouse over to where the spot is, the spectrum is lower everywhere. So this is just this is a gray spot, right? The spot is just less flux at all wavelengths.
Move around on the surface of the star. Okay, that's ridiculous.
Yeah. So with this is a spherical harmonic wavelength decomposition of the stellar surface.
Oh, wait, and is it doing the spherical harmonics in real time? How real time is that? It's pretty real time, right? It's doing the sums for you right there.
It's doing sums for you right there. Yes. Yeah.
Quick question. The fact that you use two wavelength vector is if you want, for example, to introduce a at some point and just have the same reference vector, just to set your profile if you need.
No, the reason is that when I'm computing the observed spectrum, the flux right here includes the Doppler shifted flux from over here. And so I need to have a value defined on a slightly larger grid.
Okay. So your wave zero is actually just a larger.
Okay.
I know. Okay.
And then, yeah, question.
I was just going to ask if you're going to scroll the other image.
I am.
Okay,
Yes.
cool. Nice.
And so the other image is what you see. And when you scroll it with the track, if you have a track, you can see your observed spectrum, which is the black one, wiggle around. I don't know if, yeah. Okay, sorry, it's a little slower on the projector. But that's it, right? That's the apparent Doppler shift at least due to the photometric effect of the spot. Again, I'm not modeling convective blue shift, but that's something that I really want to try to figure out to put in this model.
Now, in this model, the spot is simply the same spectrum, darker.
Correct.
You also have a functionality where you could, the spot could have
Yes.
mixing in a different spectrum.
Yes. And so this here is just the outer product of one map and one spectrum. You can have many maps and many spectra, in which case you're essentially doing a PCA decomposition of the spectral spatial stellar surface. And so it's in the documentation, we'll have a chat afterwards. This allows any number of components.
So there could be different line ratios in the spot.
Exactly. Yeah, and I'll point you to the documentation, there's an example.
That's what we need.
Yeah, so, right. Yeah. Yes. So in order to actually compute, I mean, this is basically computed the observed spectrum, but if you wanted to do this without visualizing it, I'm going to call this observed spectrum. And let me zoom back in.
This and like that could be a brighter feature of this.
This would be dot map dot flux theta equals theta. So it's same exact syntax as photometric starry maps, but this time flux really means like the time series flux as a function of wavelength, which is equivalent to the spectra as a function of time. So run that, and remember the first time it runs it, it's compiling it, and when you run it a second time, it's a little faster. Let's see. So in the interest of time, I'm just going to copy and paste some stuff from the template, because what we're going to do is we're now going to compute the rate of velocity for this hypothetical star.
Cool. Are we going to do cross correlation?
Well, I mean, this is essentially the CCF already, so we're really just going to fit a Gaussian at each point in time and compute its mean wavelength.
Yes. Cross correlation with one line.
And so this is my very fancy rate of velocity algorithm here, right? So this is my Gaussian model for the line. This is my loss function, right? I'm just comparing my Gaussian fit to the flux, and I'm just going to minimize where I'm solving for the oh, here, right. The amplitude, the mean, and the standard deviation.
You're minimizing.
Sorry?
And you're minimizing the errors.
Oh, good. Good. No, I did not. So sum pi dot optimize mean. Okay. If you're a very fast typer, you can copy it, but I'm going to scroll away in just a second. So let's do that. So let's do mu equals get line centers. I'm going to pass in the observed wavelength array and the observed spectrum. Oh, right. I forgot to pass lazy equals false when I created this map. And so you'll notice that, funny. You'll notice that this thing is not a numerical value, it's a node in a Theano computational graph. And so if I were to go back and pass lazy equals false, it would actually automatically compile this and return a numerical value. What I'm going to do instead is do the hack of just calling eval on this function. This is slower because it's not actually compiling it. It's going through and evaluating all the things in the node without any optimization, but it still works.
And then it makes rectangular data, right? Which is the size of your.
That's right. So
one direction of the number.
exactly. So observed spectrum dot shape is 100 by 100. I made the mistake of making my wavelength array the same like my time array, but I believe the first number is the time dimension. Good. And so now when I do this, good, I have mu. So these are the line centers in nanometers, because those are the units I'm using. And so to get the RV in this case, speed of light times mu divided by the mean. And then I'll just subtract the mean.
Fine.
Fine. This is not how you compute rate of velocity.
I'll accept it.
Delta lambda over lambda, MC. All right. Okay, now for the grand finale, we'll plot this and we'll compare it to the original one that we used, that we computed just doing the velocity and weighted intensity map. And so I'm going to plot theta versus RV. I'm going to label this the velocity weighted. And I'm going to plot the new one, which is Dop RV, and I'm going to label that Doppler or spectral. We did the full spectrum. And I'll add a legend. They're slightly different. I mean, we did different things to compute the radial velocity of the spot. That's true. That's true. We could do that easily.
Can you repeat the comment?
The comment was that this blue one, which is velocity weighted, may have the effect of limb darkening because I reran those cells.
Yeah.
The orange one does not. But even if it didn't have the effect of limb darkening, these still would be slightly different because
the line shape isn't Gaussian.
That's right. And so what is the radial velocity of a spot? It's still defined, and it depends exactly on how you're computing the radial velocity. So
actually, it's worthy of note that it hasn't come up yet in this meeting that the concept of radial velocity is still defined if the line shape is different in different observations.
Right.
There literally isn't an answer.
Right.
Which is kind of interesting, given that that's the main object. Something that doesn't exist.
Right, exactly. So we have 8 minutes left. Okay, so questions about this?
I guess one question I have is, have you used this on real or realistic stellar spectra, as in taking template spectra, for example, taking 2 temperatures, or actual observed spectra, like the ones that go into SOAP?
I haven't, and that's very much something that I want to chat with people about this week, to get my hands on.
It sounds like it would be a fun project for somebody.
And you literally have all the tools now to live the dream.
The problem is we could go down this rabbit hole and never come out again.
I'm still for that.
So Baptiste,
And so if now we have this line profiles that are observed line profiles, and we want to apply the inverse process, which is implemented right in Starry, how difficult is it to do so?
inverse process of what?
Like you are having basically getting the maps.
The map, yeah.
Alternating, yeah.
Yeah, it's straightforward. So I have a tutorial on that. I'll point you to it. I've also have unpublished stuff that I'm happy to share with you. Yeah. Good. Annalise.
Sorry for my voice. It's not that late, that's like. I was wondering, so you just added the one spectral line now with a bunch of assumptions that I may not necessarily agree with, but if you want to make like a larger spectrum, do you have to add line by line, or is there like how would you go about actually creating something that looks more like an actual spectrum?
Yeah, you would have a larger wavelength grid and you would add your line template as your rest frame spectrum.
She has a spectrum on her screen. She could just load that in, right?
Sure. Or you could do this on something like the CCF.
Yes.
What do you mean, like Python.load?
Like literally, you could take that as an array of numbers, and that could be your true spectrum.
Oh, okay.
Right, because it's agnostic. It's just a set of values.
Right, yeah. But I would love to chat about the assumptions that you think could be improved on.
I mean, we could make a little tutorial that actually uses a piece of the solar spectrum.
Yeah.
Yeah, that would be really cool.
So the thing I'll say, so I want to chat about assumptions because I want to make this better. And the thing that I'll say is, a lot of the motivation behind this is that in order to get from the map and the spectrum to the observed spectrum, Starry does this linearly. So that's the important part, is because what I'm trying to build towards is an effective Gaussian process model for this stuff. And the way to do that and to make this closed form and easy to evaluate is to do a linear model. And so whatever something like convective blue shift, I want to chat with Xavier about this, is I have to figure out how to linearize it in order to propagate that into the Gaussian process. Heather, yeah.
I think if you want to include convective blue shift in an easy way, and you are thinking about like a line focal or AKA a CCF, then you are less interested in like the line depth dependence that Xavier was talking about. It should actually be more interested in the center to limb variation that exists in convective blue shift.
I see, right.
And that is something that you could then be like, okay, it's a function of mu and it has some behavior, and then you can implement that into your model. And you could probably do that in some.
Good. Okay, that's good advice. Thank you.
Yeah, you could just have a limb brightened thing that has a different velocity.
Yeah, right. Yeah, right, and that's different from limb darkening, which I haven't.
And it should be F squared.
What should be F squared?
The convective blue shift part.
Okay, got it. Okay, thank you.
We could have a really, really boring session at the pub tonight and actually.
If I have the energy.
So actually, while we're talking about the pub, for those who'd said they would like to come on the Riverside Walk, I'm trying to ask myself, the pub that we were going to is mainly a sort of outdoor place, and it's kind of cold.
Yeah.
Shall I try and find an indoor place?
No.
A place with indoor options?
Yeah.
Okay. How far are you prepared to
Our
walk?
phone started to fail last night.
And how far of a walk do people want? Like, we're talking 2 kilometers, 5 kilometers, 500 meters.
All the way to Cambridge.
Sorry?
All the way to Cambridge. No.
Are you that eager to get away?
It's hard for the Canterbridgians.
Yes. Oh, okay. No, I will try to find an alternative that is big enough for us all to.
So I think I have like 3 minutes. So last 3 minutes. So both starry and starryprocess are on read the docs. If we go to starryprocess.readthedocs.io, the second tutorial is just going to go through one of these examples. So I encourage you to have a look at this week. The thing about starryprocess, it doesn't actually, I haven't yet implemented the radial velocity side of things or the spectral side of things. In principle, it is as easy as, like, you take the covariance matrix of the spherical harmonics from the starry process and you linearly transform it to spectral space via that design matrix, which you can compute using starry. One of the issues is that the linear problem accounts for the fact that when you have a spot, your overall intensity in your spectrum is lower, just because the total amount of flux coming from the star is lower. The step that we usually do of normalizing that, or measuring, because like when you take a spectrum, the overall calibration is not usually well known, and so you might as well just normalize it to 1 or to the continuum or whatever. That step is nonlinear, right? Because you're normalizing something to itself, right? You're dividing two random variables. And so that step is tricky to incorporate into the Gaussian process framework. And so currently what you have to do is you need a latent variable for every epoch in your spectrum, which is the overall dimming or overall brightening due to the current spot configuration in view. If that didn't make any sense, don't worry about it. If it made half sense, I'm happy to talk about it some more, but that's one of the implementation hurdles, just like TMI at this point. But if you're interested in photometry, starry processes should be plug and play. And the idea is that you just import starry process, you generate an object. This is now a Gaussian process that's equipped with a log likelihood and so forth. And the parameters of the Gaussian process are the things that I talked about, such as the radius, the width of the radius distribution, mu and sigma, the latitude and standard deviation of the spot latitude. Altium, A and B can also be used to specify the latitude. Fractional spot contrast, number of spots, so forth. This is all in Theano again, and so you need to either evaluate it or explicitly compile it. There's some instructions on how to do this here. But basically there's instructions here on how to sample from the Gaussian process, how to compute the flux from those samples. So that's just sample from a Gaussian process, condition on some stuff. Those are 50 samples. But then the interesting part is the inference, right? So if I'm actually given a light curve, I want to learn what the Gaussian process parameters are. And so here, this is a light curve. We compile the function. I'm going through this very fast and I apologize. It's on the tutorial.
You're going to learn, the inference you're going to do is in those parameters about like what latitude the spot is.
That's right. That's right. And so here's just inference in 1D, where I can just do a for loop. And so from that single light curve, I've learned something about the spot radius. There are degeneracies, but it's consistent with the truth. And so this isn't as relevant to you guys, but the code will evolve in the next few months to be able to model spectral time series, and the interface will be. But still, if you're interested, it's still worth going through that. I'm out of time, I think.
I think if people want to have time for coffee, which we probably need. But it's very, very.
I'm very good at typing.
To cover. You wanted to cover.
Yeah.
That was